All right. So we're going to continue from the previous lesson and learn about conditional probability. Before we do that, let me show you this table, guys, and let's understand and how to read this table. This is called a contingency table. I like to teach a conditional probability with an example. Students get it from the example right away. Okay, so this is a table, guys, that shows results of a study in which researcher examines a child IQ and the presence of a specific gene in the child. So they did research on the IQ and the presence of a special gene in the child. Can you guys tell me what does the number 52 represent here? This is a total. It's a total from the row. What does it represent?
It's the high IQ.
All the children who have high IQ, 52 of them. Can you guys tell me what 72 means here?
It means the gene present.
Yeah, it's all the children who have the gene present, including the ones with high IQ and with normal IQ. So remember, the total represents the total of this. The 30 represents the total of all children who don't have a gene. Can you guys tell me what the 102 represent?
Total of all children.
Total of all children, exactly. So that's very important to understand that. And one more question. Can you tell me what 33 represents?
The high IQ children with the gene present.
Yes, it's the number of children who have high IQ and also have the gene present together. And okay, very good. So now I think we can start answering some questions. This is one of my favorite ways of proposing probability questions using a table. So do expect, guys, to see probably a table like this on the test. We're gonna begin with part B, which is something that you've done already. So we select a child at random. What's the probability of selecting a child with normal IQ?
50 out of 102.
Okay, so the grand total is 102, guys. Remember, the denominator is all possible outcomes. I agree. Now, normal IQ, your friend says 50 because she looked at the total of normal IQ and she said 50, which is correct. 50 out of 102. It will be wrong to say 39, guys, because 39 is not all the normal IQ. It's a normal IQ and the gene present. It's wrong to say 11 because 11 is a normal IQ and gene not present. We want all normal IQ, regardless whether the gene is present or not present. So 50 out of 102. Okay, I'm gonna add one more question here. What is the probability, before I go to the remaining part, the conditional part? What is the probability of selecting a child with normal IQ and gene present?
It's 39 over 102.
Exactly. So normal IQ, guys, and gene present. Look what I would do if I were you. Draw an arrow here. Draw an arrow where the two arrows meet. It will be your numbers, 39 over 102. All right. Now, let's look at part A and C. They're different, guys. There is a condition there, and I'll tell you what do I mean by a condition here. I'm putting a condition in here. We select a child at random. What's the probability that the child has a high IQ given that the child has the gene present? So I'm telling you guys, you're gonna select from the children who have the gene present. I said given. When I say given, this is a condition that you already have to make sure that it is already taken care of. So what would be the probability of selecting a child with a high IQ, given that the child already have the gene present? Take 30 seconds, guys, think about it, and then we'll discuss the answer. Just write it down on a scrap paper, the answer, and then we'll share it. I'm gonna give you about a minute to think about it. Okay, guys, what do you think the answer is? It's a fraction.
33 over 52.
33 over 52. Any other answers?
No, I think it's also 33.
So it's
52.
32 over 102.
Well, if you say 33 over 102, you're picking from
Oh,
all the children.
mean-
But we said
I
we
mean-
put a condition.
33 over 72.
Aha, 33 over
Sorry.
72. And that is the correct answer. And
Because
let
it's
me,
talking about the gene present.
exactly. So look, guys, I put a condition here. I said, given that the child has the gene. So actually we single out the children, the ones who have the gene and the one who don't. And we need only, we have to pick only from the children who have the gene, because that's the condition who he put on us. How many children have the gene present, guys? 72. You can see here. And now, we want out of those 72, the favorable outcomes will be the ones who have the high IQ. Well, how many are there who have the high IQ? There are
33.
of them. So, look, guys, I'm gonna show you how I teach students to figure this, to figure out the answer. Very easy way without even referring to the formula that I'm gonna give you. I'm gonna give you the formula, guys. I'll write it down, but I'm gonna show it to you verbally. Look, how do you figure out this answer? Whatever comes after given goes to the denominator. So what comes after given here? The child has what? The gene. So you figure out how many children have the gene. It's 72. You put it in the denominator. That's number one. Now the numerator, look what you put in the denominator. You go to the high IQ row and the gene present column and see what the intersection is, and you put this in the numerator. So look, this is the high IQ, this is the gene present. Where the two numbers meet, it will be your numerator, and then you can figure out the answer this way. So it will be a 33 divided by 72. I'm gonna show you, demonstrate this to you guys in part C, and you're gonna see how we're gonna do it. Find the probability that a child has the gene, given that the child has a high IQ. Do you guys, I don't want you to think that these are the same question. I swapped, the conditions. So, given that the child has a high IQ, I told you what comes after given goes to the denominator. So how many children has high IQ, guys?
33.
No, total of children who have high IQ.
52.
52. That goes in the denominator. Now we want the number of children who have high IQ and have the gene present. It's the same thing, 33. So the answer will be 33 out of 52. Any questions here, guys? I'm gonna give you another part. I'm gonna add one more just to make sure that we understand how to do this. So I'm gonna add part E. I want the probability of normal IQ giving gene not present. You see what comes after given, you have to find the total of gene not present. How many are there that don't have the gene present?
30.
11 over
30.
50.
Not 50, it's 30. Gene not present. And now we want the normal IQ and the gene not present together. How many are there who have a
11
normal
out of 30.
IQ and gene
11.
not present? What did you guys say?
11 out of 30.
11 out of 30. Exactly. I hope that's making sense to you guys. So the gene not present, it's coming here. And the 11, guys, is the intersection of the normal IQ line and the gene not present line. You just do the normal IQ like this, guys, watch. And gene not present, and where the two lines meet, that will be your answer, which is 11. Okay, let me swap him, guys, and tell me what would be the answer. What is the probability that the gene is not present given a normal IQ? So,
Would
probability.
that be 11 out of 50?
Gene, let me write it down. Probably you're correct. Given normal IQ. All right. So probability of gene not present, guys, given normal IQ. I told you what comes after given has to be in the denominator. Always, always, always. So normal IQ, what's the total of normal IQ? You are correct, it's 50. Now intersection of gene not present and normal IQ, we found out earlier it was 11. The answer is 11 over 50. So when you guys have a conditional probability, your denominator will never be the grand total anymore. It will be the 102. Any questions? Okay. Let me show you the formula that we use here. But you really, guys, if you understand what I just said, you really don't need to use the formula at all. You can, guys, mute from your side. Let me mute everybody. All right. Okay. Here's the formula, guys, that you might come across in the book. But if you understood the idea, you just follow, just what I said. If you have two events, when you find the probability of A given B, this is event A and this is event B. In the book, instead of the word given, they write it like this. And that means given. Probability of A given B. What I told you guys you do. I told you what comes after giving goes into the denominator. So this is the probability of B. And what goes in the numerator is the intersection of the two. The intersection, we use the word and. Probability of A and B. So probability of A given B, guys, it's the probability of A and B together divided by the probability of B. And that's the formula for the conditional probability. I'm gonna write it down right here so you can see it in the notes. And that means this line means given. All right. Any questions, guys? So this is about conditional probability. I usually, when I ask questions about conditional probability, I'll give you a table. So if you follow exactly the same techniques that I did here with the table, you guys, you should be okay. Okay, independent events. It's what the word says. Two events are independent if the occurrence of one event does not affect the probability of the occurrence of the second event. If two events, so that means if one event happens and the second event happens as well, the two events have nothing to do with each other. For example, if I tell you it's very cloudy outside, that's one event, and event B, it's gonna rain. Well, these two events are not independent because when it is cloudy, probably this is a sign of rain. So you cannot say that these two events are independent. But if you roll a die in one hand and you toss a coin in another hand, these two events are independent. They have nothing to do with each other. There's two different tools that you are using. So then you can treat them as independent events. So just use common sense, guys. If you feel that the two events are dependent for a good reason, you say they are dependent. If they are independent, they are independent. So let me just go walk you through an example, guys, and check with you whether the events are dependent or independent. Okay, a standard deck of cards, guys, has 52 cards. And there are 4 suits. Each suit is 13 cards. There is clubs, spades, heart, and diamond. And there are 4 kings in a standard deck of cards. Please remember that. And then there are 4 queens in a standard deck of cards. So the probability of selecting a king at random, if I show you 52 cards, guys, and tell you close your eyes and select, a card, and I ask you what's the probability that you selected a king, you tell me it's 4 out of 52. 52 is the possible outcomes. There are 52 cards. Now the ones that will work in your favor, only 4 cards that have kings. So you say 4 out of 52. And it is the same for the queen. It's 4 out of 52 as well. So let's read this example, guys, and tell me whether you think the events are dependent or independent. You select a king from a standard deck of cards, and you don't replace it. Not replacing it means you don't put it back. And then you select a queen from a standard deck of cards. So event A, select a king, select a card. What's the probability of getting a king? You don't put the card back in the standard deck of cards. And then the second event, select a card. What's the probability of getting a queen? Do you guys think that the events are dependent or independent?
Wouldn't it be dependent? Because when you take the card out, then you change the odds of getting the queen.
You got it. You nailed it. You guys, when you select the first card, the chance of selecting a king is 4 out of 52. But when you don't put the card back, you're not working with 52 anymore. You're working with 51. And now the probability of selecting a queen is not 4 out of 52. It's 4 out of 51. And that is against, just the true definition, just of probability, because the probability of a queen is 4 out of 52. Because you did not replace the cards, the events are not independent. They are dependent. Exactly what you said.
So it would only stay, or it would only be independent if the number didn't change?
Exactly. So if I said, look, listen to me here. If I said you replace it, you put it back, then they will be independent. But because I said you don't replace the card, you're working out of 52 1, then it's not, the events are not independent anymore.
Okay.
Events, that's exactly right, are dependent because the probability of selecting a queen is now 4 out of 51 and not 4 out of 52. It should not change, but it changed, and that makes the events dependent. Okay, what about number 2, guys? We talked about it earlier already. We toss a coin and get a head. What's the probability of getting a head, guys? When you toss a coin. 1 out of 2. You agree? It's 1 out of 2. And what's the probability when you roll a 6-sided die and obtain a 6? What's the probability of getting a 6 when you roll a 6-sided die?
1 out of 6.
Okay. What do you think of the events? Do they have anything to do with each other?
No.
No, independent. Okay, here's a third example, a verbal one. Event A, you drive a BMW. Event B, you get into a car accident. What do you think of the events?
Dependent?
Why?
Dependent.
Why?
Because you don't have a car anymore, you got in a crash.
No, no.
When you bought the car, you gotta expect to have a crash.
Exactly, because you're driving a sports car. No one buys BMW, guys, to drive below the speed limit. Trust me. So it's like, that's why the insurance, guys, on sports cars is a lot higher than the insurance, just on bigger cars or family cars. So if you drive a BMW, it's likely that you're gonna speed up a little bit, and as a result of speed, accidents happen. So the events are dependent. That is I mean, you can argue otherwise, but it will be a difficult argument not to argue that nobody, just will speed with a sports car. So these events will be dependent. Okay, you have a jar of candy. This is a fourth example. Pay attention, because that might come up today, just in the Socrative activity. You have a jar of candy. There are 15 pieces of white candy and 15 pieces of red candy. Event A, you select one candy and you check whether it's white or not. And then you eat it. And then event B, you select a candy and you want to find out whether it's red. Are the two events dependent or independent? Remember, 15, 15.
Dependent.
Dependent. And let me tell you why, guys. The probability of selecting a white candy is 15 out of 30. But then on the second draw, the probability of selecting a red candy is not 15 out of 30. It should be 15 out of 30 also, because I have 30, and because you ate one, now your total is not 30. If your denominator changes, guys, as one of your classmates said earlier, if your denominator changes, the whole thing is going to change. So then the events are dependent. That's what I want you to know about events, dependent and independent events. All right. We'll continue with this. Okay. If two events are independent, guys, I'd like you to memorize this formula. This is very, very important formula. I mean, you'll have access to it always. If two events are independent, the probability of A and B together happening, it's a probability of A times probability of B. And I'm going to show you an example and how to use this formula. A coin is tossed and a die is rolled. Find the probability of getting a head and then rolling a 6. So we need the probability of a head and 6. Okay. You guys, you agreed with me that tossing a quarter and rolling a die are independent events. We just did it. That means the probability of rolling a head and a 6 means the probability of a head times probability of getting a 6. What's the probability of getting a head, guys, when you toss a coin?
1/2.
Yes. And what's the probability of getting a 6 when you roll a die?
1/6.
1/6.
1/6. And if you multiply them, guys, you get 1/12, and that's the answer. Now, another students could tell me, I want to do it this way. I want to list all the outcomes and see how many outcomes will give me a head and 6. You could do it. You could have done it this way, guys. Watch. You list the outcomes. 1 with the head, 1 with the tail. 2 with the head, 2 with the tail. 3 with the head, 3 with the tail. 4 with the head, 4 with the tail. 5 with the head, 5 with the tail. 6 with the head, 6 with the tail. You count them, you get 12. And there is only one that has 6 in the head. That's what we want. So it will be 1 out of 12. But look at the time you saved, guys. You didn't have to go through this if the events are independent. You just multiply the probability of each event and then you get your answer. So this is what how you work with independent events. Okay, let's do this example here, guys, together with independent events. The probability that a knee surgery is successful is 0.85. So a doctor perform, knee surgeries, and the chance of success is 0.85. What's the probability that three different patients will do 3 surgeries and all 3 surgeries are successful? My first question to you guys, are the 3 surgeries, there are 3 events, do you think they are independent?
Yes, because one of them's not gonna work.
No, not because of this reason, because there are 3 different patients. They have nothing to do with each other. Each one has a success of 85%. Yes, the events are independent. How do you find the probability of 3 surgeries are successful? Remember, there are 3 events here. Any ideas how we figure out the answer? What do I do?
Because there's still a chance 85% that will work.
Okay, so what do you do with the 85%? Since the probability of success for each patient is 85%, and the 3 patients are independent. So what do you do with the 0.85?
Multiply it by 3.
Yeah, multiply it, not by 3, by itself 3 times.
Yeah.
That's it. And that's how you figure out the chance. Let's multiply it. .85 times 0.85 times 0.85. It's 0.6141, guys. So if you have this question on a test, guys, and I tell you 4 patients, what's the probability that all 4 surgeries are successful? You do 0.85 times 0.85 times 0.85 times 0.85.
Sir, I have a question.
Yes.
So we can't put like 0.85 times 3. We have to put 0 times.
Definitely, because 0.85 times 3 means 0.85 plus 0.85 plus 0.85.
Oh, okay.
Never add. Remember that. And try it, Stan. If you multiply, you're going to get an answer over 1. It's impossible to have an answer over 1.
Okay. Thank you.
Yeah. Okay. Now I'm going to change this one. That none of the surgeries were successful. What is the probability, guys, that none of the surgeries are successful?
0.
No, there is a probability of failure. So
0.003.
how do you figure this out? What do you do?
0.15 times 0.15 times 0.1.
Exactly. You see, guys, the probability of success is 0.85. The probability of failure is 0.15. So let's see what's the chance that this doctor is going to perform a surgery on 3 patients and all 3 surgery are going to be not successful. Well, the probability of failure is 0.15. Does everyone understand where I came up with the 0.15? Because 100% subtract the 85%. And 100% minus 85%, guys, is 0.15. So it will be 0.15, 0.15. Okay, let's see it. Don't add them, guys. It's a multiplication. Okay, 0.003375. It's a very low probability, guys, that this is going to happen, but it's not 0. There is a chance that 3 surgeries, just will be not successful if a doctor performed them, but the chance is very, very low. Look at that one. I want to take an opportunity here, guys, and do some algebra. If my math lab asks you to change this to a percent, guys, how would you change this to a percent? What do you do to change it to a percent?
0.003 times 100. I think.
Okay, so we need to multiply by 100%. And when you multiply by 100%, you move the decimal point 2 digits to the right. So it will be what? 0.3375%. You see, guys, It's not even 1% chance of the 3 surgeries, all 3 surgeries won't be successful. It's a very low chance. It shouldn't happen. If this percentage was high, guys, this doctor will go out of business if that's a chance of performing no successful surgeries. Okay, if I ask you to round this to 2 decimal places, guys, what would be your answer? So 2 decimal places, we want 2 decimals right here. So what's the next one? 7. So we get one more here, so it will be what? Point what? 34%.
34%.
Yeah, just be very careful with it, guys. And this is how we change a person. This is pretty much what you need to know algebra in this chapter.
I have a question.
Algebra. Yes.
So I didn't get it. Why it changed to 0.34? Because the voice cracked. I don't know why.
Oh, okay. Look, we need to round this to 2 decimal places.
Okay.
So 2 decimal, you look at the third one. If the third one is 5 or more, you add 1 to the second one and then drop the rest. Well, since 7 is 5 or more, so I added 1 here.
Okay, thank you.
Okay. Now, guys, we're gonna tell you what we mean by mutually exclusive events. 2 events are called mutually exclusive if they cannot happen at the same time. So I'm gonna write another definition here. 2 events are called mutually exclusive if they cannot happen at the same time. Some students sometimes forget about not, and they think they can happen at the same time. No, events are mutually exclusive if they cannot happen at the same time. I'm gonna give you some examples, guys, and tell me whether you think the events are mutually exclusive or not mutually exclusive. So I'm gonna start. Pay attention. I'm gonna do some verbal examples, and then I'm gonna project some examples from the textbook to show you how can you tell if events are mutually exclusive or not. But pay attention now, listen to me. Event A, select a student from my class who is a nursing major. That's event A. Event B, select a student with brown eyes. Are the 2 events mutually exclusive or not mutually exclusive?
They're not.
They're not mutually exclusive because they can happen at the same time. Is it possible to find a nursing students who have brown eyes, guys? Yes. Or no? If your answer is yes, that means the events are not mutually exclusive. Exactly. Here's another one.
Can I ask a question?
Go ahead.
Why would it be mutually exclusive?
Not mutually exclusive here because they can happen. Not mutually exclusive, I said, because they can happen. It is possible to find a student who is a nursing major and also has brown eyes. If you cannot find, if you cannot have those 2 events happen at the same time, then they are mutually exclusive. But if not, they're not mutually exclusive. Here's another example. Selecting a student whose birthday is in May, and event B, select a student whose birthday is in June. Is it possible to find the same students whose birthday in May and June? Yes or no?
Yes.
Yes? How could someone's birthday be in May and in June at the same time?
Oh, no.
I'm talking about the same student, remember?
Oh.
So no, these are mutually exclusive. Here is another third example. Selecting a student with blood type A+, and selecting a student who is a female.
That's not mutually exclusive.
Not because it is possible to find a female student whose blood type is what? A+. So if you can find the two events happening together, guys, then they're not mutually exclusive. If they cannot happen together, then they are mutually exclusive. And just one more second, I want to show you some more examples from the book. Just give me a second to get the book. This is on page 162. If you go to the textbook online, it's page 162 if you're taking notes. Okay, number 9. No, first of all, 7. Mutually exclusive or not mutually exclusive? Lost the popular vote, won the election.
Not mutually exclusive.
No.
Yeah, because you see there's an intersection between the two. You see the intersection? That means they can happen at the same time. Remember, mutually exclusive cannot happen at the same times. Event A, movies that are R-rated, and Event B, movies that are rated PG-13. What do you think here, guys? They are mutually exclusive because you can see you cannot have a movie that's rated R and rated PG-13 at the same time. It's either R or PG-13. What about 9? Randomly select a female public school teacher. Randomly select a public school teacher who is 25 years old. Mutually exclusive or not mutually exclusive?
They're not.
They're not, because you can find a female public school teacher who is 25 years old. Ask yourself, guys, is it possible to find someone who belongs to event A and event B at the same time? If your answer is yes, then they're not mutually exclusive. We did number 10, guys. You cannot have the same students born in April and May at the same time. We're not talking about two different students. We're talking about intersection. It's the same person. What about 11, guys? Randomly selecting a person who is Republican and randomly selecting a person who is a Democrat. Is it possible to find a person who is a Republican and a Democrat at the same time?
Yes.
No.
I mean, no.
No, they don't allow that.
Mm-mm.
I think you can get in trouble, you know, just for doing this. They do a research, you know, on that person before even they belong to one party. So these are mutually exclusive. What about 12?
Not mutually exclusive.
Yeah, because you can have a US senator who is a member of the Congress. So this is an example, guys, of mutually exclusive events. This is what we mean by mutually exclusive events. I wanted you to just understand that. And we're gonna go to the next rule, addition rule. And that would be almost toward the end of that chapter. Okay, so I'm gonna go back to my handout. We understand what mutually exclusive events are. And we're gonna do this example now before I get, now we're doing a rule, it's called the addition rule of probability, which I'm gonna explain it right now to you guys. So I'd like you, just to pay attention to this example that I'm gonna put and help me answer the questions, okay? Remember I said the sample space is the collection of all outcomes. They usually use the simple S for the sample space. So I'm gonna put those outcomes in the sample space. Let's say these are all possible outcomes. Just put some numbers there. Okay, I'm gonna circle this and call it A, event A. And I'm gonna circle this and call it B. So A is an event. It has 5, 12, 6, 4, 13. B is another event. It has 7, 4, 13, 3, 11, and 10. And S is the sample space, is all the outcomes, all the possible outcomes of the experiment. For example, if you roll a die, guys, the sample space will be a 1, a 2, a 3, a 4, a 5, and a 6, because these are all the possibilities. If you toss a quarter, the sample space will be head and tail only, two outcomes. Okay, here's my first question, guys, to you. What is the probability of selecting a number that turns out to be an A? So you would win if you close your eyes and select a number from the sample space. What's the probability of selecting a number that turns out to be an A?
5 out of 12.
Okay. You said 5 out of 12. Let's see how many do we have altogether. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I agree. And how many are in A in your favor? It's 5 out of 12. Does everyone agree with this answer? This is very important, guys, to get to what I'm trying to get to, the addition rule, in a second. Now, the second question, guys. You select a number at random. What's the probability that this number will land in B, will be in B?
6 out of 12.
Let's see how many are in 12, in B. 1, 2, 3, 4, 5, 6. Actually, this one should have been inside, but it just turns out to be, put it outside, 6 over 12. Next question. What is the probability of selecting a number that turns out to be in A and B together? What do they have in common, guys?
Same denominator.
Same denominator, doesn't change. 12, because you're selecting from the sample space, which is 12. And how many are there in A and B together at the same time?
2.
So we put 5 plus 6.
No, just A and B, not A or B. I'm coming to A or B. A and B means it is in A and in B at the same time. So I see only 2 numbers that are in A and B at the same time, which is 2 out of 12.
But why is it out of 12? Shouldn't it be out of just what's in A and B?
But actually, when you close your eyes and pick a number, you're picking it from S always, the sample space. Not picking it from A and B. You're just picking, let's say I put those numbers in a basket. You're picking from a basket that has all those numbers always. So once you say I want to pick only from A, you're not doing probability anymore, because you're looking at the numbers in A. You're not supposed to do that. It's done randomly. Randomly means without looking. So now, guys, we'll come to the new stuff, and I'm going to explain what A or B is. A or B, guys, means you will have success if you get the number, if you get the number to be in A or in B, but not necessarily both. In the previous one, it has to be in both in order to work. But now, guys, if your number turns out to be in A, you have success. If it turns out to be in B, you have success. If it turns out to be in both, that's okay. You have success, but not necessarily. So I would like you to count with me, guys. How many are there in A or B? Let's count them together. 1, 2, 3, 4, 5. Do I count 4, 13 again? You're not supposed to. 6, 7, 8, and then what? 9. So the answer is 9 out of 12. Now, maybe as students will tell me, why didn't you count 413 again when you went, inside B? Well, you're not supposed to. When I take attendance, guys, I'm not supposed to count your name twice. Even if you say it twice to me, I'll just mark it, just once. So the numbers are 1, 2, 3, 4, 5, 6, 7, 8, 9 over 12. Now, guys, I'd like you to look at the previous three answers. There is a connection between the previous three answers and the answers in the fourth one. There is something that you could have done without looking at the diagram and figure out this answer. What would that be? Look at the answers, guys. What would you have done with the first three in order to get 9/12?
5 plus 6 minus 2.
Exactly, that's the rule. So if you add 5 plus 6, you get 11, and you minus a 2, you get 9, and here's the rule, guys. The probability of A or B. Remember, or is different from and. And means together, intersection, or either A or B is okay. It will be probability of A plus probability of B minus probability of A and B, and this is called, guys, addition rule. So that's A or B. I'm gonna show you another example and how to work with this, guys. We're gonna go back and show you the example, the formula. Probability of A or B equals probability of A plus probability of B minus probability of A and B. Now I say further here, if the events are mutually exclusive, then the probability of A or B equals probability of A plus probability of B. Can a student tell me why I eliminated probability of A and B here if the events are mutually exclusive? If the events are mutually exclusive means, guys, they don't have anything in common. And if they don't have anything in common, that means the probability of the intersection is going to be 0. So there is nothing in common, probability of A and B is 0. Just like the two diagrams I showed you about movies that are rated R and movies that are rated PG-13. They don't have any intersection. That means the probability of A and B is 0 because they are mutually exclusive. Because probability of A and B equals 0 when events are mutually exclusive. All right, so that's a definition. Okay, let's do this example, guys, and apply the addition rule here. You roll a die. Find the probability of rolling a number less than 3 or rolling an odd number. You see the or here? This is event A, and this is event B. Okay, let's do it together. I'm gonna do it step by step, guys. And I'm gonna use the formula. What is the probability of rolling a number less than 3?
2 out of 6.
Does everyone agree that it is 2 out of 6? Because the numbers on the faces of the die that are less than 3 are 1 and 2, two of them. And it's always out of 6, guys. So now you guys, you know your denominator. Your denominator is going to be 6. It will not change. Plus probability of B. What's the probability of rolling an odd number? How many odd numbers are there on the faces of the die, guys? There is 1, there is a 3, and there is what? 5. So how many of them?
3 out of 6.
3 out of 6. Minus probability of rolling a number that is less than 3 and odd at the same time. So my question to you guys, the numbers that are less than 3, let's list them. 1 and 1. Odd, 1, 3, 5. How many do they have in common?
1.
1. So 1 out of 6. You see, guys, this is it. And the answer will be 2 plus 3 is 5, minus 1 is 4 over 6. If you were doing this in my stat lab, they probably reduce the answer, and that will be 2/3. And this is the addition rule. We're going to do another example with the addition rule, guys. The frequency distribution shows the volume of sales in dollars and the number of months a sales representative reach each sales level during the past 3 years. If this sales patterns continue, what's the probability that the sales representative will sell between 75,000 and 124,999 next month? Okay, what would that be? So between probability of sales between 75,000 and 124,999. All right, can you guys help me with this? In order to sell, so either you can sell, so what are the options for the salesperson to sell between 75,000 and 124,999? What do you guys see as options? You
7
guys,
and
you agree with me that it could be this? Would that work for the salesperson? We want him to do more than 75,000, but less than what? 124,999. So it will be either this one or what? The next one. He can do both at the same time. So you either make a sales up to 100,000, or you can make sales from 100,000 to 124,999. So it will be probability of sales from 75,000 to 999,999, or 100,000 to 124,999. So what would be the answer, guys? It's an or now, so it's an addition rule. Can you help me out now, figure out the answer? So what's the probability of sales from 75,000 to 99,999?
So you would add those together?
Yes,
Um,
adding together, I got, well, actually you already mentioned how many, 36 months, I don't know, let's add him, 8, 6, 14, and 7, 21, 30, 32, 36. So that's a 36, the denominator. And what goes in your numerator here? We want sales from 75,000 to 100 to 99,999. It will be what? The 7 plus, what would it be for the 100,000 to 124,999? 9. And minus probability of A and B. Well, these events are mutually exclusive. You either can be here or there, but not both, not at the same time in both. You either can go up to 100,000 or from 100,000 to 124,000. So you get 7 plus 9, which is 16/36. And that would be your answer. Okay, so this is the addition rule. So the hint for you guys for the addition rule, anytime he asks you for a probability of an event or another event, he is talking about the addition rule. You must use the addition rule. When he says and, no, that's not the addition rule. So the addition rule, it's probability of A or B. All right. And we're going to show you a nice example. I told you I like the table. You're going to see the contingency table, and we're going to answer some questions with the contingency table. A blood bank catalogs the types of blood given by donors during the last 5 days. A donor is selected at random. What's the probability of selecting a donor that has type O or type A? So probability of type O or type A. Okay, what do I do? What does the rule say? The rule says, addition rule, it's a probability of type O plus probability of type A, and can the student continue this, minus what? Probability of what? Type O and what? And A.
IP. A, sorry.
Yeah. All right. What's the probability of selecting a donor that has type O? The total is, grand total is 409, guys. Remember that.
184 over
184
409.
over 409.
Yes, that is correct. I couldn't agree more. Plus, what's the probability of selecting a donor that has type A?
164 over
Yeah.
409.
Now, guys, that's the tricky part. Is it possible to find someone who has type O and type A at the same time?
No.
No.
It's impossible. And look at type O. Type O is a column and type A is a column. Two columns can never intersect, guys. In order to have intersection, it has to be a row and a column. And look, so that's zero. The events are mutually exclusive here.
But sir, like we can't add both, like type O and type A.
Yeah, we can. If we say probability of type O or type A, you just add the two types and that's it. But there is no intersection between the two. So your answer will be, guys, if you add 184 plus 164 will be 348 divided by 409. That's the answer.
Mm-hmm.
Now let's look at B. B, we will be able to apply the formula throughout. What's the probability of selecting a donor that has type B or negative, RH negative? So let me write down the formula. By the rule that I explained to you, it's a probability of B plus probability of RH negative minus probability of B and RH negative together. So that will be, guys. I want to make it easy on you and put the denominator already. What is the probability of selecting someone who has type B?
45 over 409.
Yep. What is the probability of selecting someone who has a negative type, RH?
65 over 409.
Yes, does everyone agree? Look what we're looking here, 65, the total. Is it possible to find someone who's type B and negative? Yes, there is an intersection, guys. Watch. Like this. Where do they meet?
8.
8. So the events are not mutually exclusive here, and just add them up. Yeah, actually that's my blood type. I'm B negative. So 45 plus 65, 110 minus 8, 102 divided by 409. Let me ask you a couple more questions, guys, before we wrap this up. We're almost to the end of this chapter. If I give you this table, I'm going to add a C here. Find the probability of selecting a type A donor and RH plus. Type A donor. Okay, what would that be? Type A and RH positive.
139.
139.
Over, yes?
344.
Over the, no, not why 344, it's a grand total, no conditions here. So
164.
139. This is RH plus, guys, positive, over 409. If you guys don't see the word given in the problem, don't even change the denominator. Your denominator has to be the grand total. Since you mentioned that, I'm gonna propose another question with a conditional probability. Pay attention to it, guys. Let me find a spot to write this one. So I'm gonna do a part E here. Probability of type A donor given Rh positive. Now we'll make you happy. We do a given one. Okay, what is it gonna be? What did I say? You're gonna follow my rule, guys. I said that what comes after given goes to the denominator first.
139 over
So how
344.
many Rh positive?
344.
344, exactly. And now, guys, it's the same thing here, 139, type A and Rh positive, 139. You see how the probability becomes larger here, bigger, because we changed the denominator, which is 139 over 344. And the last thing, have your calculator handy, guys, now. This is probably the only thing that where you use your calculator to do in this chapter, which I'm going to demonstrate to you. Just the last part. Okay. You're going to see something like this on the calculator. And let me explain. This is not a plain English exclamation mark, guys. It means something in mathematics. If you see a 4 with this symbol, it's red. 4 factorial. And let me tell you what it means. It means 1 times 2 times 3 times 4. So if I do 1 times 2 times 3 times 4, 1 times 2, guys, is 2, times 3 is 6, times 4 is 24. 5 factorial means 1 times 2 times 3 times 4 times 5. And if you do the math, guys, you're gonna get 120. But you guys, if you put 15 factorial, good luck multiplying this. It's a lot of work. 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8, all the way to 15. Well, the calculator can help here, and I'm gonna demo how to use the calculator to find those factorials. You could have in this section a simple question as simple as finding 8 factorial. You could multiply 1 by 2 by 3 by 4 by 5 by 6 by 7 by 8, but I'm going to show you a shortcut, guys, to this. So watch.
Can't you just square it with the number?
Oh, no. You will see it. You have to multiply it by the previous, by the previous, by the previous until you get to 1. So it won't work this way. So let me show you how you can do it. Let's say we want to do 8 factorial, guys. So I'll wait a few more seconds to grab your calculator. Turn it on. No need to do anything. Just put 8 here. Oh, I'm seeing the 8. Okay, now. I put 8, and look what I'm going to do now. There is a video I've made already available, shortcut in how this is done. Now I'm going to press on math. Right here. And then I'm gonna go, our chapter is probability, guys. So if you forget, remember, we're doing probability. Do you see the symbol that I'm talking about? I was talking about, guys. Do you see it show up on the screen? Which number is that?
Number 4.
Number 4. Go to number 4 and press enter. Just like a computer, guys, to execute something, you have to press enter. So press enter. Press enter again, and you're gonna get your answer. 40,320. Let's try another one. 15 factorial. You're gonna be shocked, guys, how big this number is. So put 15. math. Watch me, guys, doing math. And then probability. And ready? 15 factorial. Oh, let me write it down and show you how to read these numbers. All right, I wrote it down and let me explain how to read it. Does anyone have any idea what this means?
It's to the factor of 10 or power of 10.
Power 12. But what does it mean? What do we do?
You move
Let's
that
say
decimal
someone
place
wants
12
you
times.
someone wants you to read this number.
Infinite
What do you do? What do you say?
to the power of 12.
Not the number. The E means 10. 10 to the power of 12. What does it mean for a reader? If
That
I
means
want
you
to...
gotta move the decimal place 12 times to the right.
Exactly. You have to move the decimal place 12 times to the right. Let's move it. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't have enough. So what do I add, guys? How many zeros? I have 9 places. So I need to add
3.
what? 3 more zeros. So look, the number is... It's going to shock you guys how big this number is. That's the number. Let me see if I can read it, guys. Oh, gosh. Okay. I think it's 1,307,674,368,000. See how huge this number is? So the E12, guys, means you have to move the decimal point 12 digits to the right. If you didn't have enough digits, guys, just put zeros toward the end. If this was a negative 12, guys, it means you have to move the decimal point 12 digits to the left. I would like you to understand this from now because we're going to need it later. So if you guys get something like this on the calculator, don't ignore the E minus 3, guys, please, and put the answer as 2.74. That would be a fatal mistake. The E minus 3 means you have to move the decimal point 3 digits to the left. So look, guys, if I move it 3 digits to the left, this is 1 digit. Well, I don't have digits, so I put zeros. It's going to be here. So your answer, guys, is 0.00274. That is the answer. If you see an E minus, be sure, guys, that your answer is very close to 0. You're going to have a very small answer. And if you see an E plus, like E12, be sure, guys, that you're going to get the huge, massive number. So it's just like this one. That is what. So see the 15 factorial. Actually, probably, guys, if I try to do 50 factorial, 100 factorial, calculator will halt, will not even do it because the number is so big that probably the calculator will not be able to handle it. So don't try it now because your calculator might freeze as a result of this. So this is the factorial. Okay. Couple more things, guys, and that should be it for this lesson before I go to my handout. Okay, let me tell you what, just 2 basic things I'd like you to know in this section. That's it. Let's say I have 4 students in a class. I'm gonna label you guys as A, B, C, D. Please pay attention to this. And I want to select the 3 students out of the 4. My question to you guys, in how many ways I can select a group of 3 students from the group of 4 students? Can you help me list them? So A is 1 student, B is another, C is a 3rd, and D is a 4th. Can you guys help me list the possible ways of picking 3 students from 4? Let's begin. We need to select 3 letters out of the possible 4 letters. in how many ways we can do that. Okay. What would be a first selection, guys? Give me a possible selection.
ABC.
ABC. Okay, I want another student now, another selection.
BCD.
What is it?
BCD.
BCD. I'll go with it. That's a good. A third one.
CD and
ABD. Okay. One more.
CB and A.
CBA, you already did it.
I mean
You have
CDA.
ABC. Which one?
CDA.
BDA, we have it already. It's ABD.
CD.
CDA.
Oh, CDA, ACD. Okay.
What about CBA? It will work?
It's already there. ABC, CBA. It's the same group, same students. Student C is there, student B is there, student A. Order here is not important who comes first. So the order is not important. So how many ways, guys? Can you come up with anything else? No, guys, it's impossible. That's it. So if you have a group of 4, in how many ways you can select 3 subgroups from there? There is only 4 ways. But the order here is not important. So there are 4 ways. But guys, this can be very difficult if I have 30 students in the class and I want to select the groups of 3. Do you think it's going to be easy for us guys to list those groups? No. I start with 4 because it's easy. You can help me with that. But with 30, that's going to be a nightmare. And I don't know even if we can do it, by hand. It's a lot of work. So there must be a formula, guys, that will allow us to do this. And I'm going to show you how the formula works from the calculator. So I'd like you to have your calculator handy right now. And here's when you would use, what I'm going to show you in a second. If they give you a group of people and they ask you in how many ways you can select, just a group of 5 from this group, this is where the formula kicks in. So let's do the group of 4 and we need to select the 3 and we know the answer was 4. 1, 2, 3, 4. And then we're going to do 30 students and how many ways we can select the groups of 3. It's going to be huge, guys, but I'm going to show you how the formula can do it for you. So get your calculator ready and watch. I'm going to clear my screen. Okay, put 4 first of all, because we started with a group of 4 letters. Go to math. Go to probability. And then it's number 3, guys. N choose R. N is how many do you have in the original group, and R, how many do you want to select? So just select this one, press enter. And then enter 3, guys. You see where it's pointing, blinking? You need to enter 3. And if the answer is not 4, guys, I'm going to have to quit my job because I told you it is 4. There you go. Let's do the 30. What do you think, guys? Can you guess what the answer would be if we have 30 students and we want to pick groups of 3? In how many ways we can select the groups of 3? Do you guys agree with me that the number is going to be very big? You will see. Put 30. Go to math. Go to probability. And put 3. And there you go. Ready? There are 4,060 ways to pick a group of 3 students from a group of 30. Too many. Okay, I'm gonna put this, guys. I'm not gonna press enter. I want the students to give me the answer without doing any work. If you have a group of four, you have 4 students and you want to select all 4 of them, in how many ways you can do that?
1.
1. Yes, it's only one group. Just bring them all and that's it. That's one time. So 4 choose 4 is 1. This is called, guys, in statistics called combination. When you want to select a group from a larger group and you're asked how many ways you can do that, this is called combination when the order is not important. But when the order is important, I'm going to show you another example now. I'm going to take the 4 letters, guys, that you did earlier. In how many ways we can select a group of 3 letters where order is important now? And let me tell you what I mean by that. If I have 30 students in my class and I want to select any 3 students to help me with the task, here the order is not important. It doesn't matter which students show up first, to volunteer. But guys, if we have 30 students and we're doing an election for a president of a club, vice president of a club, and then the secretary of the club, and we're gonna elect the president, just first. So does the order matter now? Who comes first, as a president, and then who comes next as a vice president, and then secretary? Well, the order now matters because the first person to be selected is going to be the president of the club. The second one will be the vice president. The third one will be the secretary. So there are situations in life where the order doesn't matter, but there are other situations in life, like in sports, guys, like race. Do you think the order matters here? Who comes first and who comes second? Definitely the order matters here because it's critical. The ones who show up first is going to be the winner, then the second place, and then the third place. But if I just say, I want the 3 volunteer students to help with the task, whether student A or student B shows up first, it doesn't matter. Here, the order is not important. So now we're gonna list in how many ways we can select 3 letters where order is important. Can you help me? So you guys listed those for me first. ACD. Any other combinations?
No.
Let's see this. Do you guys agree that it could be also ACB? Because the order matters now. What else can I put here?
BCA.
BCA or BAC? 2 more.
CAB,
CAB. 1 more.
CBA,
Yep. What about here? BCD, BDC, CBD.
DCB.
Yes. BCD, we already put it. DCB, we're going to put that. DCB and 1 more.
DDC.
DBC. The order matters here because D could be the president, B could be the vice president, C is, he will tell you guys whether the order matters or not. So what about ABD? Let's list them.
DBA.
Okay, so we got DBA, we got DAB, we got ADB, and we got BAD, and we got BDA, and 6 here. So 6. How many altogether, guys? 24. 6 plus 6 plus 6, plus 6. But the good news, guys, you don't have to do this. The calculator can do it, and let's do it now together on the calculator. Clear the screen. Put 4. Go to math. Go to probability. Okay. We use number 4, it's factorial. We use number 3 when the order doesn't matter. And now it's number 2, guys, when the order matters. P, NPR. P means permutation, order matters. And put 3. What was the answer, guys, when we did add them up?
24.
24.
Okay. I must get 24, guys. Otherwise, I'll be in trouble here. There you go. See, we did it on a piece of paper. I showed you it was 24, and the calculator is telling me it is 24. This is called the permutation. The difference between combination, guys, and permutation is permutation, the order matters. Combination, the order doesn't matter. I'm going to show you with you a very interesting example. So you'll like this one. You have a table, a round table that seats 10 people. You're going to be shocked, guys, to find out the answer to this question that I'm going to propose. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Here's the table. You invited 9 people to your house, including you, so there will be 10. The question is, in how many ways we can seat those people around the table? We need to figure this out. Do you think the order matters here and how people sit next to each other? Yes or no? If it doesn't matter, guys, if it doesn't matter who sits next to who, how many ways you can seat 10 people around a table of 10? If the order doesn't matter, who cares? Well, how many ways?
10 different ways?
No. If
Oh,
the
there's
order doesn't matter, whomever sits, it's okay. It's just one way. No problem. But now here, we want to figure out how many different arrangements you can put in there. In how many ways you can seat people around the table. So different arrangement. It's important who sits next to who. In how many ways you can seat 10 people around a table of 10. Actually, this is a permutation, guys, but I'm going to demonstrate that to you. The first guest arrives and the table is still empty. So the first guest goes to sit. How many choices does the first guest have?
10.
9
10 choices.
or 10.
Yeah, he has 10 choices. He can sit anywhere he wants. So 10 choices for the first guest. The next guest arrives, guys. He sees one guest already being seated. How many choices does he have?
9.
9. Then the third guest arrives. And then he sees 2 people are being seated. How many choices does he have left?
8.
8. And you guys, you see 7, 6, 5, 4, 3, 2. You know who's going to be the last one to sit? The host, right? Already 9 people are seated. So how many choices does the host have?
1.
1. Using the counting principle, you multiply the events. Okay, guys, you want to see what 10 factorial is for me? It's 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10. Let's figure it out with a 10 factorial and how many ways you can seat those people in there. I'll go to probability. Gonna be shocked to see how many ways you can seat people around a table of 10. What is it? 3,628,800 ways. But guys, this is a permutation. Order is important. You could have done this 10p10. You have table of 10 and you want to see 10 people. So it's 10p10. Let's do a 10p10, guys, and see what we get. 10. Math. And the answer is going to be the same as above, guys. There you go. It's a permutation. 3,628,800. All right. I'm gonna go back to this. So guys, the combination, you don't have to use the formula by hand, but this is called NCR. You don't need to do this calculation. I'm gonna write the formula. You can simply use your calculator, just for this formula, NCR. So you just input N and then input R. This is for combination where order is not important, without regard to order. But when we regard the order, we have this formula, NPR, which is the one that's built on the calculator, is like this.
I have a question.
Mm-hmm.
Will the permutation and the factorial always be the same answer?
With the factorial, not always.
Okay.
It's just happened, just with this one. Yeah, it just turned out to be, just a factorial, but not always.
Okay, thank you.
But if it is, if R and N are the same, yes, it will be the factorial always. So if I tell you 5p5, you just do 5 factorial. If I tell you 6p6, you do 6 factorial, or you just input the formula.
Okay.
Now, guys, the last thing before we wrap this up, and I just want to take attendance and tell you what you would do with the activity. If you have 43 race cars started in the 2000 Daytona 500, how many ways can cars finish first, second, and third? Is the order important here?
Yes.
Yes, that's a P. Okay, how would you answer this question if I give you? You have 43, so you put 43 into your calculator, and then you go to math probability and you find P, and what number would you put? I mean, we're asking about 3 cars, first, second, and third. P what? 3. And that would be your answer. This is in how many ways you can finish the race. So you can do 43 P3. So that's pretty much it, guys, for chapter 4. I will be available for office hours from 12 to 1 today. But before you go, I'm going to start you on this activity, guys. And